Today we will be talking about improper integrals. First, let's talk about the two types of improper integrals. Type 1 is an integral that has infinite integral. This means it has negative infinity, positive infinity, or both as a part of the interval within the integral. Type 2 is an integral that has a discontinuity within the interval. For example, if you have negative 5 to 2 for the integral of 1 over x to the power of 5, then we know there is a discontinuity at x is equal to 0, since the function cannot be 1 over 0. Another example would be the integral of 1 plus 2x over 2 times the square root of 9 minus x for 7 to 10. We know that x cannot equal 9, or else the denominator will be 0, which doesn't exist. Let's look at some examples. In the first example, we have the integral of ln x over x from 1 to infinity. If we look at this integral, we know that it is a type 1 improper integral because of infinity at the top of the interval. So to solve this integral, we will solve it like any other integral except that we will replace infinity with t, and we will take the limit of t as it approaches infinity. So to solve this integral, we will use substitution since we have ln x, and its derivative 1 over x. We will let u equal to ln x, and du will be equal to 1 over x dx. We isolate for dx, and we get that x times du is equal to dx. Now we have limit as t approaches infinity for the integral of u over x times x du from 1 to infinity. We see that the x cancels, and we are just left with u, which is pretty easy to integrate. So we get u squared over 2. We obviously keep the limit till the end, and now we sub ln x back in for u, and we evaluate this expression from t to 1. So limit as t approaches infinity of ln t squared over 2 minus ln 1 squared over 2. Ln 1 is just 0, so we are left with ln t squared over 2. Now we know that for the ln function, as t approaches infinity, ln t will also approach infinity, meaning it will keep increasing without reaching a finite number. So this integral is divergent. Let's look at another example. Let's say we have the integral of x times e to the x squared from negative infinity to infinity. We know that this is a type 1 improper integral. Now to solve this integral, we must divide this integral into two parts because both ends of the interval are infinite values. So we will have integral 1, which is equal to the same integral, but for the interval negative infinity to 0, and integral 2, which is also the same integral, but with the interval 0 to infinity. All we did was just split the interval in half, but x times e to the x squared stays the same. For the integral to be convergent, both integral 1 and integral 2 have to converge. If one of them diverges, then the whole integral diverges. Let's start by evaluating integral 1. You can also start by integral 2. It doesn't matter which one you start with. So we will take the limit as t approaches negative infinity for the integral of x times e to the x squared from t to 0. We will use substitution to solve this integral. So we will let u equal to x squared, and du will be 2x times dx. And by isolating for dx, we get that it is equal to du over 2x. Now we plug these back into our integral, and we see that the x cancels. So we factor 1/2 out of the integral. We are left with the integral of e to the u, which has the antiderivative e to the u. We sub x squared back in for u and evaluate it from t to 0, and know that e to the 0 is just 1. So we are just left with 1/2 plus e to the t squared over 2. Now let's draw the graph of e to the t. We see that as t approaches negative infinity, e to the t approaches 0. However, it's not just e to the t. We have e to the t squared, and that squared part makes the negative infinity into positive infinity. And as t approaches infinity, e to the t is also approaching infinity. So we have 1 over 2 minus infinity, which is just negative infinity. This means it's divergent. Since one part is divergent, there is no need to evaluate the second part, because we know that the whole integral is divergent regardless of whether integral 2 is divergent or convergent. In the next example, we have the integral of 1 over x cubed from negative 1 to 3. This integral is type 2 because there is a discontinuity at x is equal to 0. To solve this integral, we will divide out integral into two parts, and the same rules as before apply. Both parts must be convergent for the whole integral to be convergent. The interval for integral 1 will be from negative 1 to the discontinuity point 0, and integral 2 will have the interval 0 to 3. We will start by evaluating integral 1. So we have limit as t approaches 0 from the left side for the integral 1 over x cubed from negative 1 to t. We flip the integral to become x to the power of negative 3, so it's easier to integrate. And know that its antiderivative is negative x to the power of negative 2 divided by 2. Now we evaluate it from negative 1 to t. We get negative 1 over 2 times t squared minus negative 1 over 2 times negative 1 squared. We simplify, and we get limit as t approaches 0 for negative 1 over 2 times t squared plus 1 over 2. If we sub the limit in, we will still get 1 over 0, which means that it does not exist, making the whole integral divergent. Let's look at another example. We have the integral of 1 over the square root of 3 minus x from 2 to 3. We know that this integral is type 2 since x cannot equal to 3, or else we will have 1 over 0. Since the discontinuity is at one of the endpoints, we do not have to split the integral into two parts. Instead, we will evaluate the limit as t approaches 3 from the left side for the integral of 1 over the square root of 3 minus x from 2 to t. So we flip the integral to 3 minus x to the power of negative half, which gives us the antiderivative negative 2 times 3 minus x to the power of half, and we will evaluate it from 2 to t. This will give us the limit as t approaches 3 for negative 2 times the square root of 3 minus t plus 2. We sub 3 into t, and we get 2, which is a finite number. This means that this integral is convergent.